Okay, good morning, everybody. We're moving into part 4 of the course, which is the final part of the course. So the topic of the remaining lectures will be, well, they're all related to Java generics. All right, so remember we've got this class called int stack, right? And int stack represents a stack of int values. Right? How did we implement int stack? So our int stack class is implemented using an array of int, right there. Right? When we push an element, right, we're always pushing an int onto the stack, and when we pop an element, we're always popping an int off the stack. If you wanted a stack of strings, you would have to, if we want to change this class so that change or have a class that represented a stack of strings, then before Java introduced generics into the language, the one solution would have been to create a separate class. Right? So now you're going to make a separate class just so that you can have a stack that can hold strings instead of ints. Right? So in other words, you would make your class string stack. And then when you look at the code of string stack, it's almost completely identical to int stack. Right? Instead of an array of int, we've got an array of string. Right? Instead of pushing an int onto the stack, you push a string onto the stack. Instead of popping a string off a stack, instead of popping an int off a stack, you pop a string off the stack. So everything that's highlighted in gray, these are the changes that you would have to make to the int stack class. Right? Which isn't very many, right? It looks like the only changes we're making are one to a name and to some types. Right? If you look at this a little further, you'll see that this is true even inside the methods. Right? So if you look at the pop method, right, what do you have to change in order to make our int stack work with strings instead? Well, I have to change the return value. Right? But then when you look in the code, there's almost nothing here that depends on strings. Right? The only thing that depends on string is this variable element. Right? And you can even get rid of this variable if you wanted to. Right? Down here, you could return the appropriate element from the array. Right? So again, there's very few changes that you have to make this stack of int become a stack of string. Right? And in fact, when you look in this a little further, the only things that you have to change are related to the type declarations. Right? Basically, you take string and substitute that in places where you used to have int. Right? Now, if this is really the only change that's being made, it would be nice if the compiler could do the substitution for us. Right? So that in other words, I don't have to, or the programmer doesn't have to go to the trouble of copying their existing class, changing their types. Right? It would be nice if you can tell the compiler, hey, I want this stack of string, and here's how I want to do it. And that's exactly what generics are for in the Java language. If you know C++, that's what templates are for in the C++ language. Okay, now before generics were introduced to the language, then you would do this a different way. Right? So instead of making a stack of int and a stack of string and a stack of double and a stack of date or whatever, right, you would make a single stack class. The element type would be big O object. Right? So you can do stacks, queues, lists, maps, right? All of these things. Right? So where you needed a collection where you wanted to have a collection of a different type, you would just store object references instead of storing specific type references. Right? And this is also easy to do. So if I wanted to make a class representing a stack of objects, right, well, it's the same as making a stack of string. Oh, this is going to use a list. Okay, this is going to use a list. All right, so if I wanted to do a list-based stack that can hold any reference type, right, you just use a list of object. Right? Why does this work? Because I can put anything into a list of object. Right? Everything is substitutable for object in Java. Well, every non-primitive value is substitutable for object. So I can store whatever object I want in this list of object. Right? Nothing really changes here. Right? The types change. Right? You push an object onto the stack. You pop an object off the stack. Right? And that, I mean, otherwise it looks exactly the same as any one of our other stack classes. And so this is what you'd used to do. Right? If you wanted a generic collection, you would just make the collection the element type object. Right? This has an unfortunate consequence, though. Right? So when you use this particular class, right, whenever you pop an element, you get back an object. And that's inconvenient because that means when you pop the element and you want to use it for something, you have to cast it to the type that you are expecting is actually on the stack. Right? And so in other words, right, here's my list object stack. I'm going to store some strings on it. Right? So I push the string hello, konnichiwa, and hello onto the stack. Everything's fine. Right? Those strings are all objects, so I can push those onto the stack. If I want to pop an element off the stack and turn it to uppercase, right, I can't just pop the element, right? Because when I pop the element, I end up with a big O object, right? And big O object has no to uppercase method. So what you end up having to do is you pop the stack, cast the result to the element type that you're expecting, store it in a variable, and then use that variable to call the method that you want. And this is fine, right? It's a little inconvenient, right? But maybe that's the price we have to pay for being able to write one class and being able to store whatever I want on that stack. Right, so that's slightly inconvenient. Now, not only is it inconvenient, it's not type safe. Right, so the more serious problem with this is that you can put any reference onto the stack. Right, so I can make a stack that's supposed to hold only strings, but there's nothing that the compiler can do to help you prevent people pushing an int or a double or, an integer or a double or a date or a list onto the stack. Right? Because your stack can hold anything. This is the same problem that you encounter in Python when you use a Python list or any other Python collection. Right? You can put anything you want into that collection. Right? Useful, right, if you are very careful about what you put into the collection. Right? Unsafe because there's no guarantee that someone else might not put something that they're not supposed to into that collection. Right? And so in Java, Java tries very hard to ensure type safety. Right? So in other words, whoops, sorry. Right? So here's an example of, this is an example of what can happen when you use a stack of strings. A stack of object. Right? I've got my string stack, which is supposed to hold only strings. So yes, I can push strings onto the stack, but I can push the number 1 onto a stack. Which is weird because that's a primitive, and you can't put primitive values into a collection, right? But this works because Java auto-boxes the 1 to an integer. You can push another stack onto the stack, and you can push a date onto the stack, even though the name suggests that it's supposed to be a stack of strings. Right? If you're willing to live with this, then you can just use then this is a perfectly fine approach to implementing a generic collection. Right? If you want type safety, then you have to do something else. Right? So the fact that any element type can be pushed onto a stack makes it impossible to write type-safe methods that operate on collections of objects. Right? So what does that mean? It means you can write a method that seems to be correct, but only if your collection has the appropriate types in it. Right? When you write these methods and programs, any method or program that uses those methods will appear to compile. Right? So in other words, the Java compiler will compile this code cleanly and not indicate to you that there's any problems. The problem is when you run the program, it may fail. So here's an example of a method that takes in a stack, and it looks like it's supposed to be a stack of integer, right? Because that's why that's the name of the parameter, right? It's int stack. So the method is called sum and clear. What the method is going to do is it's going to sum the elements in the stack and remove all the elements from the stack. Right? It's going to return the sum as its return value. Right? So this is easy to implement. You just pop the elements off the stack and you add them to the running sum. Right? So there's my running sum. While the stack is not empty, pop the stack. Right? Now remember, when you pop the stack, you get back an object. So if I want to add the value of this element of elem to the running sum, I need to cast. Right? So cast the element to an integer and add it to the sum. This is fine as long as you pass in a stack whose elements are only integers or are convertible to integers by this cast. Right? The problem is as soon as you pass in, say, a stack that has a string on it, that cast fails, and now your method throws an exception. Right? So this method has a pretty strong precondition on it. It's that that stack can only hold integer values. And there's nothing that the compiler can do to enforce the fact that this stack should only have integer values. Right? So in other words, the only time you can catch errors in this with using this method is at runtime. Right? And you'd much rather prefer to catch the errors at compile time. Okay, so there is the designers of the language eventually got around to fixing this issue. Right? So in version 5 of the language, the designers of the language introduced generics into Java. Right? So generics allow you to parameterize a class, interface, or method over types. So what that means is that you can make a type be a variable in your class, right? Or look like a variable in your class. Right? So like when you use a list of date, right? When you pass in that, or when you specify that you want the type of the element to be date, right? That's parameterizing the list over a type. Right? This lets you, instead of creating separate classes, right? Like int stack, string stack, date stack, et cetera, et cetera, et cetera, you make one class, right? Where the user specifies the element type that they want to use. Right? And so you're used to the syntax by now because you've been using lists and sets and maps since early in the course. Right? So you make a stack of integer, right? Instead of writing int stack, you make a stack of string instead of writing string stack, stack of date instead of date stack, and so on and so on and so on. Right? Now the advantage of this approach is that Java's generic type mechanism is almost completely type safe. Right? You have to try very hard to break type safety. So to make a generic class, it turns out it's not very hard to do. At least it's not hard to do mechanically. So in other words, the syntax isn't terrible. At least not if you're making a simple generic class. Right? So if you have a class and you want it to be generic, right, then all you do, it's the same as declaring a regular class, except you add the angled brackets, right, after the class name. Inside the angled brackets, you list the types, the names of the generic names of the types that you want to use. Right? So something like T1, T2, right, T3, T4, T5. Right? If you have 5 generic types that you want in your to use in your class. So the angled brackets here, these are called the parameter section. Right? They specify the type parameters. The type parameters can be any non-primitive type. Right? So when someone uses your class, they can specify any non-primitive type for the type parameters. So when you name these type parameters, you tend to give them very, very short names. So in other words, the names tend to be 1 letter long, or sometimes 2. Right? So if you're making a collection of elements, right, and you want your collection to be generic, then the element type is normally called E to indicate that it's an element. Right? For maps, right, where there's a key and a value, so there's 2 generic types in maps, right, then you would normally use the names K and V, right, short for key and value. If you make some collection that represents where the generic types are numeric, right, so you can imagine taking our point2 class and letting people choose what type they want for the coordinate type. Right, so our point2 class uses doubles to represent the coordinates. But you could turn the class into a generic type and and let the user specify what the coordinate type is. Right? So someone might have points that are integer coordinates, someone might have points that are long coordinates or float coordinates, et cetera, et cetera, et cetera. If you're in that situation, you can use the name n for number. And then in general, if you just want a generic type name, you can use S or T or U or V or W, X, Y, Z are all very common. T1, T2, T3, T4 is also very common. Okay, so let's make a very, very simple generic class. So probably the simplest generic class that you can make. Right? Now in Java, you can only return a single value from a method, and sometimes this is inconvenient. Right? So if you want to find the max or the min of a collection, right? Number 1, you want the maximum or minimum value. Number 2, if it's a list, you might want the index of that value. Right? You might want to change the value or something like that. Right? So you might want to know where the value is located in your collection as well. In Python, this is easy to do. You just return a tuple. Right? The first element of the tuple is the min or max. The second element of the tuple is the index. Right? So I can't return a tuple in Java, but I can make a class that represents a tuple, right? Or in this case, a pair, right? So a pair of values, right? And it's easy to do, right? I can even make it generic, right? So my class pair is a generic class. Right? Its generic types are T1 and T2. Right? It's got two fields, first and second. Right? They're both public, so anybody using this class accesses these directly, right? Because really you're just using this to return two values. Right? So first and second, the type of first is T1. The type of second is T2. Right? So this lets someone return back a string and an integer, or a double and a date, or whatever you want. Right? Whatever the two types they are. They can be even the same type, right? So you can return a string and a string. And now you can write your max or min method that returns the maximum or minimum value and the location in the list where the maximum or minimum value occurs. Whoa, sorry. Right, so my method max takes in a list of integer in this case, right, and it returns a pair, integer, integer. Right? So the first element of the pair is going to be an index. The second element of the pair will be the maximum value, right? The maximum value, right? So if the list is empty, there's no maximum value, so we throw an exception, right? Otherwise, we make a pair to store the result, right? The index of the maximum value is 0, right? The maximum value we set as the, why is that I? Sorry. T get 0. There's another mistake somewhere here. Result for, no, T get I. Okay. All right, so the maximum value, we just assume it's the first value in the list, right? And now we look at all the elements in the list, all the remaining elements in the list, right? So we get the second element in the list. If it's bigger than the current maximum value, set the index of the maximum value to I, right? And then set the maximum value to the current element. Right, and away you go, you loop over the whole list, and then when you're done, you found the maximum value and its location in the list, so you just return the result. Right, and so there's a very simple example of making a generic class that's actually useful. Right. All right, any questions so far about creating a generic class? Right, so basically, the only thing you have to do is indicate the generic types. Right. Okay, so if I want to turn my array-based stack into a generic array-based stack, right? Step 1, add the generic type variable, right? So after the name of the class, in angled brackets, put in the generic type, right? This is a stack is a collection of elements, so we use the name E for the generic type. Right, now I'm going to use, this is an array-based stack, so what is the element type of the array? Well, it's an element of type E, right? For pop, I guess for push, right? You're going to change the, when you push an element onto the stack, the type of the element will be E. When you pop an element from the stack, the return type will be E. Okay, so that looks like it's going to be easy to do, right? We're just going to change a few types, which used to be string, I think, to E. Right. Okay, now this works until you get to the constructor. Right. So in the constructor, when you try to make this new array, right? What's the element type? Well, it's E, right? Because we're in a generic class. Right. So if you try to make a generic array, you end up the compiler indicates that this is an error, right? And it tells you you're not allowed to make a generic array, which is inconvenient. Unfortunately, that's the way it works in the Java language. Right, so that highlighted line on this slide, right, causes a compilation error. Right? So in Java, one of the limitations of the generic types is that you cannot make an array of generic type. And this is because generic types were introduced into the language after quite late, right? So it wasn't until the 5th version of the language where we got generic types. And it turns out that if you try to make a generic array, bad things happen, given the way that the rest of the language is defined. right? So it looks like we're stuck, right? Looks like I can't make an array-based stack, but that's not true, right? We know from the previous solution that if I make an array of object, this will work just fine because I can store whatever I want in an array of object. So the solution is instead to make an array of object. Right? So back here, change that E to big O object. Right? Java's perfectly happy making an array of object. Right? So I can now make my array of object here. Right? Okay, now in Java, arrays are said to be covariant. Right? So what that means is that arrays, the array types are special in Java. Right? So in Java, if you have an array of object, right, and you have an array of string, right, then it turns out there is a relationship between these two types, which is kind of surprising. Right? And so it turns out that an array of string, you can think of that as being inherited or extending an array of object. In other words, an array of string is an array of object, right? Or an array of string is substitutable for an array of object. Or an array of string is a subtype of an array of object. Right? And so that's what it means to be covariant. Right? An array of stuff is substitutable for an array of its supertype. Right? So that means the following compiles. Right? If I make an array of integer, right, can I store it in a reference that's an array of object? Right? The answer is yes. Right? That is a subtype of that. Right? Or that's a superclass of that. Right? So that compiles. Which seems it might be useful. Okay, now if I take my array, right, and I set the first element of the array to the string hello, does this compile? Right, and so you think, well, I don't know, maybe, right? So you've got the string here, right? What's the element type of objs0? Well, it's object. Can I store a string in an object? The answer is yes. Right? So this actually compiles, even though, right, that array objs is actually an array of integer. Right? So what this lets you do is that the compiler lets you do this. The compiler lets you store a string, right, into an array of integer. Right? But the only reason it lets you do this is because it never looks at the runtime type to determine whether or not this line is legal. Right? So remember how declared and runtime types work in Java. Right? The declared type tells you what you can do with the variable. Right? What's the declared type of objs? Well, it's array of object. Right? Can I store a string in an object? The answer is yes. So as far as the compiler is concerned, this works just fine. Right? Does it run? It does not run, because at runtime, the Java virtual machine tries to store the string hello in a string of integer. In an array of integer, right? And that doesn't work. Right? So this error isn't caught until runtime. So you have to be a little bit careful when you're using when you're using arrays of reference type in Java. Right? Weird stuff like this can happen. Right? So arrays are covariant. Generic types are not. So if you have a list of something, like a list of object, right, and you have a list of string, there is no relationship between these two classes, right? None. So there's no inheritance relationship, there's no aggregation relationship, there's no association, there's nothing, right? They're two completely separate classes, right? So for any two distinct types, T1 and T2, a list of type T1 is not a subtype or a supertype of list of T2, right? There is no relationship between those two classes other than that they're both lists of some type. Right? So generics are invariant. So you have to remember these two things, right? Arrays are weird. This also seems weird to a lot of programmers, right? If I've got a list of string, why can't I pass that to a list of object? Right? They're both lists, and I know strings are substitutable for objects. How come I can't pass them in? The answer is because that's just the way it works in Java. Right. Okay, so if you try to do the following, this does not compile. Right? So if I make an array list of integer and try to store that in a reference whose declared type is list of object, this does not work. Right? Generic types are not covariant, so you can't do it. This does not compile. Right? This actually saves you from problems like this later on. Right? And so that's why generic types are not, that's why generic types are invariant. Okay, so back to our generic stack class. So we have an array of object as our storage type. So to implement push and pop, it turns out you need very, very minor modifications to those methods to get those to work. Whoa, sorry. So here's push. Right, now push, where are the changes here? So there's change number 1. Right, so instead of int, right, our element type is now E. Right, nothing changes up here. Right, we're just storing an element in an array, so nothing changes. The only other change is here. Right, so if I push an element onto the stack and there's not enough room in the array, I have to reallocate the array. Right, my array type is now no longer an array of int, it's an array of object. So that thing there changes. And that's it. Everything else is the same. Right, so I only had to change that, and everything works. What about pop? Well, when I pop an element from the stack, right, I return an element of type E, right, that's my element type. So what else changes? All right, so here on this line, right, where I get the element that I'm supposed to return back to the caller, right, that type right there, right, is big O object, right, because my array is an array of object. Right? But the method needs to return an element whose type is E. Right? So I cannot substitute object for E. Right? I can substitute E for object, but I can't go the other way around. Right? The only way to go the other way around is with a cast. Right? So I have to tell the compiler that, hey, this thing here in this array really is an element of type E. Right? So cast the element type to E, and then store that in the variable element. Right? Without that cast, this doesn't compile. Right? You'll get a warning too when you do this cast. So the compiler will indicate that this is possibly unsafe, right? Because you're taking something that's in an array of object and casting it to this type E. Right? You can put anything into this array of object, so this might not work. Right? Now, it's guaranteed to work in this case because your push method only takes in elements of type E. Right? And there's no other method that changes the array. So in this case, this warning is you can safely ignore this particular warning. Right? And other than that, nothing else changes. Right? So I change the return type, right? Change the element type here, and add the cast. Right? And I now have a fully generic array-based stack. Right, so perhaps 7 or 8 changes to the class, all of which are very minor, and you've now fully generified your class. Right, can we do the same thing to the interface? And the answer is yes, you can easily do the same thing to the interface. Right, so our current interface for stack is for a stack of string. I can easily make it generic, I just have to change string to E everywhere. Right, so here's our original stack interface. Right, push takes in a string. Right? Pop returns a string. To make this generic, no problem. Add the generic type up here. Change string to E here. Change string to E there, and you're done. Right? So 3 changes, you now have a generic stack interface. Right? So turning an existing class into a generic class is normally straightforward. Finally, right, we can finally take our array-based stack class and now say that it implements the generic interface, right? And we will have a fully generic array-based stack class, right? So array stack E implements stack E, and there you go, right? And now we've got a fully generic array-based stack that implements a generic interface. Right? So that's how you implement a generic array-based stack in Java. Any questions? Right. Okay. There is another lecture, there's another deck of slides. Where are they here? Okay, so we learned how to make a generic array-based stack. Can we make a generic class of some other type? The answer is yes. It's not that hard, right? So we're going to use we're going to implement some generic queues now, right? So the reason for doing this is that we can practice implementing generics, right? We can practice using arrays, and then I think we're going to do a node-based queue as well, right? So you get more practice implementing a node-based structure. A queue is a lot like a stack. Behaves a little bit differently, but it's still a linear sequence of elements, right? So that's an example of a queue, right? It's just a line, right? You've got a front of the queue, and you've got a back of the queue, right? When you enter the queue, you enter at the back, right? When you exit the queue, you exit at the front, right? Unless you're a VIP or something like that, in which case you can normally skip through the queue somehow, right? In other words, you might be able to enter at the front. Right? Now, those are called priority queues in computing science, but that's a different story. Those are harder to implement. So you probably look at those at in CISC124, the data structures course. Classically, like stacks, queues only support two operations. NQ, that's where you get into the queue at the back. DQ, that's when you leave the queue from the front. Right? So NQ is sort of like push. DQ is sort of like pop, right? The difference being they happen, where in a stack, things only happen at the top of the stack. In a queue, things happen at both ends of the queue, right? So it's slightly harder to implement a queue compared to a stack, right? Like stacks, you can have additional operations, right? And it's very common for practical queue implementations to have extra methods, right? So you might want to know how many elements are in the queue. Is the queue empty? You might want to get the front or the back of the queue without removing that element, right? So that's often called peak or front or back. You might want to know, does a queue contain a particular element, right? And so on and so on and so on, right? Equals, hash code, toString, and many other methods that you can think of. Right? So what does this is a picture of of how a queue works. Right? So in an empty queue, we've got these, I guess, these pointers, F and B for front and back, right? So they're pointing to the front and back element of the queue, right? In an empty queue, they point at nothing because there's no elements in the queue. Right? If you enqueue an element, right? So I queue an element into an empty queue, then front and back both point at the one element that's in the queue, right? So if I enqueue another element, is this going to work? Right? Then the back pointer, right, has to be updated, right? So add the element to the end of the queue, update the back pointer, right? Enqueue another element, right? So add the element to the queue, update the back pointer, right? Notice that the front pointer never is not affected when you enqueue an element to a non-empty queue, right? It is affected when you enqueue an element into an empty queue, right? So when the queue is empty and you add an element, right, now you have to update F and B, right? If the queue is not empty, you only update B, right? So it's only B that changes when the queue is not empty, right? So most of the time, when you enqueue, the only thing you have to do is adjust B. Right? Now when you dequeue, right, so I'm going to dequeue the element at the front. Right? So I'm going to remove the element at the front. Right? So when we dequeue that element, right, that element gets returned back to the caller, and then F has to now point to the next element in the queue. Right? So in this picture here, this is showing you what happens in a physical queue. Right? Everybody moves forward in the queue. Right? In our actual implementation, we're not going to move the elements forward. We're going to move F. We're going to move F in the array or the list. Right? If you dequeue again, hello, okay, dequeue again. Right? The first element comes out, and then you adjust F. Right? Again, dequeue the first element, adjust F, right? And so on. One more time. Okay. When you dequeue the last element from the queue, right, the E comes out. The E comes out, there we go, right? And now F and B both point at nothing, right? So normally when you dequeue an element, we end up updating F, right? You normally don't update B, except when the queue becomes empty. When the queue becomes empty, you have to update B as well. Right? So there's actually there's a special case when you NQ, there's a special case when you DQ. Right? When you NQ, normally you only adjust B, except when you NQ into an empty list. Right? When you DQ, normally you only adjust F, except when the list becomes empty. Right? Then you also have to adjust B. Queues are what are called first in, first out data structures, or last in, last out data structures, right? So FIFO or LILO. The first element in the queue is the first element that comes out of the queue, right? That's different than how stacks work, right? The first element into a stack is the last element to come out of a stack. Right? It turns out these two properties are useful when you start to design algorithms. That's for CISC124 though. So queues are widely used in computer science and computer engineering, so they are useful. Any website that you use that you're buying something from has got queues all over the place, right? So you imagine buying something from your favorite web shop, right? There could be lots of people trying to buy the same item, right? All of the requests for that item, they go into a queue. Otherwise, so that's to prevent, so the first person who tries to buy the item is the first person, will actually get the item. Web servers use queues to service requests, right? So again, imagine your favorite website, lots of people trying to access the website, right? Each request to access the website gets serviced from a queue. Right. Your operating system is essentially responsible for distributing resources to running processes, right? And the resources on a computer are finite, right? You have finite memory, finite CPU, finite disk, finite network bandwidth, right? All requests for these things go into queues, right? You need to print something, you go into a printer queue, right? The process needs to access the disk, goes into the disk queue, et cetera, et cetera, et cetera. Network devices use queues to determine which packets to service. So on your router, there's a queue that determines which network requests get highest priority. Right? If you're trying to stream video, then typically those packets that represent the video content get higher priority. Right? So that's to prevent choppy video from happening. There are many algorithms that work using queues. There's an entire branch of mathematics called queuing theory. I guess it's applied mathematics called queuing theory that looks at the theory of queues. Right? It's easy to make an interface for queues, right? Well, it's easy to make an interface in general. Right? So what does our queue interface look like? I want it to be generic, right? So I have the element type E. We've got a size method, right? We have isEmpty. NQ, DQ, front, and back, right? So front returns the front element of the queue without taking it out. Back returns the last element of the queue without taking it out. Right? Notice that the isEmpty method, we can actually implement it in the interface, right? Because to check if a queue is empty, you just look at the size, right? The size is a method in the interface, so I'm allowed to use that method if I want to implement the method in the interface. Right? When you implement the method in an interface, you mark it as default. Right? So any class that implements the queue interface gets the isEmpty method for free. Okay, now implementing a queue with a list is pretty much identical to implementing it for a stack, right? Using a list to implement a stack, sorry. Except that you have to remember DQ removes the element at the front of the list. Right? So how do you implement this using a list? It's pretty easy, right? Use composition to hold the list. Right? My list is going to be called little q. Right? What does the constructor do? Well, it makes a new array list. Right? What does size do? Well, you just return the list of the size of the list. Right? What does NQ do? So NQ adds the element to the back of the queue. Right? So I can just use the add method. Right? So add the element to the back of the list. What does DQ do? DQ removes the element from the front of the list. Right? So DQ removes element 0 from the list. Now remember how array-based lists, or how array list works? Right? It's a list that uses an array to store the elements. Right? If you remove the first element from an array-based list, you have to shuffle all the other elements up one position. Right? So DQ, using an array-based list, oops, right, is guaranteed to have big O of n complexity, because you have to move the remaining n minus 1 elements forward one position in the array. Right? And that might be computationally, that might not be acceptable if you need a very fast queue. Right? Throw if empty, that's just a method that checks if the queue is empty and throws an exception if it is. Right? So you can't dequeue an empty queue, throw an exception if it's empty. Right? What about front? Front just returns the element at the front of the queue. Right? If there's no element, throw an exception. Back simply returns the element at the back of the queue. Right? If the queue is empty, throw an exception. ToString is pretty easy if you use a list, because you can just call the list version of ToString and get the list representation as your string. Right? So it's pretty easy to implement with an array, with a list. Right? If you choose to use an array-based list, though, you end up with an onDQ method. Right? NQ is also worst case on, because every once in a while you have to expand the size of the list. Right? Or you have to expand the size of the array that the list is using to store the elements. So worst case here is also on. Most of the time it's O1. Right? Okay, now I would like to make DQ not be on if I can help it. Right? In other words, it would really be nice if DQ could be O1, right? Or O log n, or something better than on. Right? You really don't want on. Right? We're going to try to implement this thing using an array. Right? And you might think, well, look, if you have an array list, it's using an array too. Right? So, and an array list, you just told me that it's big O n if I DQ. Right? Can we really make an array-based list, an array-based queue have an O1 DQ? Right? And the answer is yes. Right? But you have to be a little bit clever about how you do it. Right? So the queue implementation is a little bit more sophisticated than the stack implementation. Right? Now remember, in a queue, things happen at both ends of the queue. Right? In the stack, things only happen at the top. So in our stack implementation, we had a field that represented the top of the stack. In a queue, we need fields that represent the front and back of the queue. Okay? We need an array to hold the elements of the queue. We need to keep track of the size, right, the number of elements in the queue. So front, that's going to be the index of the element currently at the front of the queue, right, except in an empty queue. But we'll get to that in a second. Back will be the array index of an element currently at the back of the queue, except in an empty queue. Okay? So when we make an empty queue, it's going to look like this. Right? We have an array of some size, right? Not necessarily 16, but I'm using 16 in these pictures. Right? In the empty queue, front is going to point at some element of the queue, not necessarily 0. Okay? You have to keep that in mind. So it's not always 0. But in our constructor, we can make it point at element 0. Right? Back is going to point at element -1. Right? So the value of back is going to be -1. In other words, back is going to be an invalid index for our array. Right? So that's how we're going to. That would be one way to keep track of this of whether or not the queue is empty. Okay, so there's our empty queue. How do you NQ an element? So to NQ an element, I need to add something to the back of the queue. Right? In the empty queue, I'm just going to stick the element right there. Right? So NQing an element, it's going to be similar to pushing an element onto the top of the stack. Right? So number one, if the length of the array is equal to if array length equals size. What does that mean? Array length. That's a typo, sorry. Oh. Sorry. Okay, if the length of the array is equal to the size of the queue, right, that means you're out of space. Right, so there's no more room in the array to hold the new elements, so you have to expand the size of the array, copy the elements over into the new array, and then adjust the array field. Once you do that, or if there is space in the array, we're going to move back one position to the right. Right? So I'm going to move that to 0. Right? And then I'm going to set the element at array back to the n-queued element. Right? So if you n-q the A, right, back was here. Right? I'm going to move it one position to the right, and then I'm going to change array back to the element that I n-queued. Right? So we're going to put the A here. Right? If you n-q another element, right, you take back and you move it one position to the right, right, and then set the element at that index to the n-queued element, right, and so on, and so on, and so on. Right? So there's your queue after n-queuing 5 elements. Right? Now, how do you dequeue an element from the queue? Right? So one way to dequeue an element from the queue is to return the A, is to remember that this is an A, and then move the B, C, D, and E forward one position. Right? But I don't want to do that. Instead, what I want to do is I want to remember that this is an A, and then move front to the right. Right? So I'm going to remember the value of the element to return. Right? I'm going to null out the position in the array. Right? I'm then going to move front one position to the right, and then I'm going to return the element that I remembered. Right? So in other words, remember that you have the A that was here. Right? Null out that element, move front one to the right, right? And now I've got a queue of size 4. Right? DQ again, right? So I'm going to remember that that's a B, right? Null out the element, move front one to the right, and then return the B. Right? And so on, and so on. Right? So if I DQ 2 more elements, front and back both point at the E, right? And I've got a queue of size 1. Oops, sorry. Okay, if you DQ one more time, right, and you just follow this process, right, so I'm going to remember that this is an E, I'm going to move front one to the right, right, and I'm going to null out that element that's there, right, you end up with this picture here. Right? So this looks like, this looks similar to the original empty queue, right, where back was one position to the left of right. Where back was one position to the left of front, right? So this looks like one way that you could determine if the queue is empty, right? If front minus back equals 1, the queue is empty. Turns out that's not true, which you'll see in shortly, right? Okay, if I n-q another element, right, you end up with the following picture, right? So back moves in this case, right? Back always moves when you n-q, right? Okay, oops, sorry. Now, if I n-q 10 more times, right, back ends up at the end of the array. Right? Can I n-q more elements? The answer is yes, right, because I've got all of these empty spaces at the front of the queue. Right? So to n-q another element, you just make back wrap around. Right? So back wraps around to the front of the array, right, and now back is less than front. Right? In other words, back is looks like it's to the left of front. Right? Here it's to the right. Right? Now it looks like it's to the left. Right? But this is still a valid queue. Right? But what you have to remember is that these quantities front and back, they're going to be cyclic quantities. Right? 0, 1, 2, 3 to 15, 0, 1, 2, 3, 4, 5 to 15, and so on and so on and so on. Right? So these values all wrap around. And so there is an example of a full queue. Right? If I keep on n-queuing 4 more elements, if I queue 4 more elements, the queue is now full. Right? Notice that back is one position to the left of front, which also looks like is also what happens in an empty queue. Right? So if back is one position to the left of front, the queue might be empty, and it might be full, and there's no really reliable way to determine which is the case. Okay, okay, so the same thing happens with front, right? If I DQ 10 elements, or 11, right, front ends up at the right-hand side of the array, right? If I DQ again, front just wraps around, right? And now we're back in the situation where back looks like it's to the right of front again, right? And so you can envision all of this as a circular array. Right? So all I'm going to do is I'm going to take this array and I'm going to wrap it around so that the two ends join, right? And draw it as a circle, right? So this is the same array as this, right? Front is here, back is here, right? Every time you NQ, back just moves clockwise, right? So if I NQ another element, back moves here, right? And it just keeps on going around. Every time you DQ, front moves clockwise, right? So if I DQ the Q, front moves to the R, right? And it moves clockwise as well. Right? So one way to draw this is as a circular array. Right? Now in a circular array, you have a fixed number of elements. So we want to address that in the next lecture. Okay, so it's 20 after. Does anybody have any questions about today's lecture? No? All right. I guess I'll see you tomorrow morning.